Welcome to my GTC 2021 talk entitled Thrust and the C++ Standard Algorithms. My name is Conor Hoekstra, and today we're going to be talking about the Thrust library of parallel algorithms and how that compares to the C++ standard algorithms. Before we get to that, a couple things I want to mention. One is that I will be in the chat. While this is a pre-recorded talk, I'll be here to answer your questions that you have. And note that even if I'm not able to answer your question live, I will be able to respond to it throughout GTC. So be sure to check back if you do ask a question and don't get an answer immediately. And second of all is that all of the slides that you're going to be seeing for this presentation can be found on my GitHub page under the Talks repository. There's a subfolder for GTC 2021. You can find all of the code samples for both C++ and CUDA Thrust code there, as well as the slide deck if you'd like to follow along there. So let's hop into the agenda for the talk. We're going to break up this talk into 5 sections. The first is the introduction, where we're going to introduce what Thrust is and what the C++ standard algorithms are. I am sure many of you will be familiar with both, but just in case, I want to give a short recap. The second section will be focusing on the difference between Thrust and C++ standard algorithms, specifically the algorithms that exist in the Thrust library of parallel algorithms versus the C++ standard algorithms. Then we'll take a look at a small gotcha to be careful when you are refactoring C++ code that uses reductions like std_accumulate to Thrust code that uses reduces. And the last 2 sections, we're going to focus on some really useful utilities that don't exist in C++ in terms of what the standard library offers, but does exist in Thrust. So specifically, that's going to be the stencil overloads of a subset of the Thrust algorithms, and then also fancy iterators. So this is the About Me slide. I have a podcast, which I co-host with Bryce Lelbach, a fellow NVIDIAN, where we talk about everything tech. I have a YouTube channel. I am the organizer of a programming languages meetup. And on top of that, I am a programming language enthusiast. But most importantly, I work for NVIDIA on the Rapids team, where we are building a set or suite of open source libraries under the Rapids name, which are focused on accelerating the end-to-end data science pipeline on the GPU. So all of this can be found at the following links. So if you want to check out Rapids, check us out at rapids.ai, and then also the links to my personal projects you can find below that. And with all that said, let's hop into the introduction of this talk. So what is Thrust? Let's first focus on this. So Thrust is a parallel algorithms library which resembles the C++ standard algorithms. So very simply, it's basically just algorithms that can run on both the host and the device, aka the CPU and the GPU, that are modeled after the C++ standard algorithms. So the rest of the information you can find verbatim on the Thrust github.io page. Visit that to check it out. If you're not familiar with the C++ standard algorithms, very quickly, these are an algorithm library that define functions for a variety of purposes, such as searching, sorting, counting, and manipulating data that operate on ranges of elements. So specifically before C++ 20, this was typically defined by a pair of iterators, your begin and end iterators. But now in C++ 20, we have ranges, so you can actually just pass it a container that satisfies the range concept. And you can find the algorithms in C++ in 3 headers: algorithm, numeric, and memory. Most of them exist in the algorithm header, but there are several that exist in numeric and memory. If you would like further resources to learn about Thrust algorithms or C++ algorithms, I can point you to several videos. So the first one, C++ Seasoning in 2017, was given by Sean Parent. This is one of my favorite talks of all time, and I can't recommend it highly enough. The first third of it focuses on algorithms and why you should avoid raw loops. The second is a talk by Marshall Clough, who is one of the implementers of libc++, which is the library that ships with Clang. And this was given at CPPCon 2016, where he talks about not only how to use algorithms, but also how to write your own. And then finally, at CPPCon 2018, Jonathan Bacara gave an overview of the 105 STL algorithms in just under 60 minutes. I myself have given 2 talks on the topic. The first one was given at C++ Now in 2019 called Algorithm Intuition, and then the second one was first given in 2019 at Meeting C++, and it's called Better Algorithm Intuition. As terms of thrust talks, the only 3 that I was able to find, the first was given in 2014 by Jared Hoekstra, who was one of the initial implementers of thrust. He gave a talk called Parallelizing the Standard Algorithms Library. In 2014 as well, he gave a talk at GTC. It was initially called Inside Thrust, and it takes a look at building parallel algorithms with bulk. And then more recently in 2019, David Olson gave a talk entitled C++17 Parallel Algorithms on NVIDIA GPUs. And all of these talks that I just mentioned, the 8 of them focusing on both C++ algorithms and thrust algorithms, can be found at the same repository where the slide deck for this talk is. So I have a references.md markdown file that not only has all of the links to these talks, but also slide decks that don't have accompanying talks, articles, and blog posts that talk about the thrust parallel algorithms and C++ algorithms. Moving on to the second section of our talk, we're going to focus on the difference between the thrust parallel algorithms library and the C++ standard algorithms. So there are several algorithms that exist in thrust that do not exist in the C++ standard library. And those primarily are the following algorithms. So we have 8 on the screen: gather, gather if, scatter, scatter if, sequence, stable partition copy, tabulate, and transform if, as well as 12 by key algorithms that we're going to take a look at in a second. So although this is a pre-recorded talk, we can have a sort of a little bit of a play along. And one of the algorithms that's currently listed on the screen actually exists in the C++ standard library under a different name. So I'll wait a couple seconds for you to try and guess in your head, and then I'll reveal the answer. So the answer is thrust sequence, if you guessed that, and the corresponding algorithm that this is in the C++ standard library is std_iota. So I guess when we were designing thrust back in the day, we thought iota was not a very good name, which is sad because it comes from APL, my favorite language, which we will see a few code snippets from in this talk. But we renamed this algorithm to thrust sequence. So note that when you see thrust sequence, you can just think std_iota from the C++ numeric header. Moving on to the by key algorithms, there are 12 of them. As you can see, it's a pretty exhaustive list, and these algorithms are super useful. We're going to take a look at an example of how to use one of these, but you can basically think of them as segmented versions of their corresponding algorithms. So when you have an inclusive scan by key, this is exactly like an inclusive scan, but instead of doing it on a whole range, you're doing it on segments of a range, which can come in handy in many, many cases. So when you combine these with the 8 that we saw previously, we have 20 algorithms currently in 2021 that exist in Thrust that don't exist in the C++ standard library. So now what we're going to do is we're going to take a look at 3 different problems that can be solved by using one of the 20 algorithms that you are currently looking at on the screen. So 3 problems. Let's take a look at problem number 1. So once again, this is going to sort of be a play along. I will wait a couple seconds after I ask each question, so you can try to answer that question in your head before I reveal the answer. So the first problem is, what do you get when you combine std_iota plus std_transform? Or in other words, in Thrust speak, what is thrust sequence plus thrust transform? So really, these 2 algorithms combined to make a single algorithm that we just saw on the screen. The answer to this question is thrust tabulate. So this is a super interesting algorithm that I actually learned the behavior of in preparing for this talk. So I knew this algorithm existed, but I did not know what it did, and I was quite surprised to figure out what it did. So a good example of illustrating what you can do with this algorithm is a really, really simple problem of just generating the first n odd numbers. For our purposes, we'll generate the first 10. So one of the ways that you can do this in C++, note that there are many ways to do this, but one of them, naively, would be to basically construct a vector and fill it first with 0 to 9 using the iota algorithm, and then transforming those values by multiplying each one by 2 and then adding 1 to it. This is a pretty idiomatic thing to do in classic array programming languages. However, and so like I said before, you can do this several different ways. You might be thinking in your head it'd be better to do a generate_m. I realize that there's many ways to solve this problem, but this is trying to highlight how you can transition from using iota and transform together to just using a thrust tabulate. And the thrust tabulate version of it looks like this. So it's only a single call to one algorithm. where we pass it the begin and end iterator for our odds vector, and then we're just using the exact same lambda that we did in our transform algorithm, and it's operating on the underlying indices as we iterate through this range. So I thought this was pretty neat to learn and to highlight an algorithm that doesn't exist in the C++ standard library. So note here that this code is not running on the GPU. This code is running on the host, aka the CPU. And it is worth highlighting, as I mentioned before, thrust algorithms can run on both the host and the device, aka the CPU and the GPU. So for the purposes of this talk, I'm going to be showing code that runs on the host. However, it's very easy to translate this code into code that is running on the device or the GPU. So if we go back to our tabulate example, here we're using a std vector, and then we're just using a thrust algorithm. And whenever you have a container that has memory that is living in the CPU, it's going to be run on the CPU. So, but the way that you fix this is just moving the memory from the host to the device. So the way that we can do this is using thrust device vector, and then just by annotating our lambda using an __ device __. So it's a very small surgical change that you have to make, just adding a thrust device vector and then the device annotation on our lambda, and this is now running on the device. So for the purposes of slideware and keeping the code simple, I won't be using thrust device vector and the device annotation, but it's pretty simple to add these to each of the examples in order to get it to run on the GPU. Moving on to problem number 2, that is going to be using one of the 20 algorithms that we saw on our screen previously. This problem is how to copy every other number. And so this can be done with a single algorithm. And this is actually a really, really useful algorithm that comes in handy a lot of times as soon as you learn it and are aware of it. So I'll wait a couple seconds. And the answer is thrust gather. So the example that we're going to look at is a very naive example where we are trying to deal cards from a deck to someone. So you can imagine in a certain card game where 2 players, you want to deal every second card to a single person. And so the code for that might look something like this. So note, we don't have a full deck of cards. We only have 6 cards in our deck that are represented by numbers that correspond to, you know, the King of Hearts, the Queen of Hearts, etc. And then we have what's called a gather map, which is going to represent the indices that we want to gather into a basically target container, which is going to be called hand in this case. So because we want every other number, we're going to be using the indices 0, 2, 4, and if we wanted to copy more or gather more cards for a larger deck, we would just add more indices. And then once we have this, we basically just make a call to thrust gather, where the first 2 iterators define the gather map. The second begin iterator defines sort of the source that we are gathering from, and the third begin iterator defines the target that we are gathering to. And once we have done this, we're basically doing a kind of variant of copy if, but instead of using a predicate to define what we're copying, we're using a list of indices to define what we're copying. And this, like I said before, comes in handy all the time once you sort of learn the algorithm and start to look for it. So with this example, the output is going to be 13, 14, and 6 because those are the elements that exist at index 0, 2, and 4. So I would highly recommend looking into gather and also its sibling algorithm scatter because, like I said, these come up everywhere. Moving on to our third and last problem from our second section on differences. This is one of my favorite problems, and it's actually a variant of a problem that I showed in my very first talk at C++ Now 2019 entitled Algorithm Intuition, and it's called Maximum Consecutive Ones, otherwise known as MCO. So this is a very simple problem to describe, but it's not so simple to solve. So basically what you're given is a sequence of ones and zeros, and you need to identify the greatest contiguous or longest contiguous sequence of ones in this sequence of numbers. So in this example, the answer is going to be 4 because that is the longest contiguous sequence of ones that we can find. So I will once again pause for a couple seconds for you to think about which algorithm you would use from Thrustland in order to solve this. And note that you actually need 2 algorithms. One algorithm at the end, which wasn't on the screen, but the primary algorithm that's doing most of the work was on the screen. If you were thinking thrust reduced by key, you are indeed correct. So basically what we're going to be doing here is identifying the segments by the contiguous equal elements, then summing up those segments, and then identifying the largest sum of those segments. So an example might look like this. Here we have a simplified version of the sequence that we saw before where the result is still going to be 4. And the first thing we're going to do is we're going to identify the segments, then we're going to do a plus reduction on each of those segments, and then we're going to call a max element at the end to get the maximum value. So here we're being a little bit tricky because typically when you call a segmented reduction, aka any of the by key algorithms, you're going to have a set of keys and a set of values as 2 different inputs. But here we want both the keys and the values to be the same thing, which is our vector of 1s. And so once we do that, basically we're going to get 2 results, one for keys output and one for values output. And here we only care about the values, which are going to be the sums. The keys are just going to be alternating 1s and 0s. So we can discard those using a fancy iterator called the discard iterator, which we'll talk about more at the end of the talk, or closer to the end of the talk. But once we've done this, basically we're going to have a vector of 3 sums corresponding to the sum of the first segment of 1s, which will be 3, the second 0, which will be 0, and then the third 1s, which will be 4. And when we call our max element on the sums vector, we'll get back the maximum value. So this is a super useful algorithm, sort of being used in a trivial case here, but this is actually pretty powerful because you can much more easily solve this in a functional language, but functional languages will actually typically take a call to 3 or 4 algorithms in order to solve this, whereas with thrust algorithms we're actually solving this with only 2 calls to algorithms, which is pretty cool. And talking about pretty cool, I said we would see some APL in this talk, and this is our first APL snippet. The equivalent version, or how to solve this in APL, which stands for A Programming Language. It was a language invented in the 60s, which is my favorite programming language. I'm not going to explain this, but just note that this is the equivalent of the thrust code that we just saw here. So typically APL code, you'll see one-liners to solve complicated problems because of the power of the primitives. So everything that is in green is a function or an algorithm, and everything in orange is an operator. So when you compose these together, you get super expressive expressions. So to highlight, we saw 3 examples, one of thrust tabulate, one of thrust gather, and one of thrust reduce by key. Like I said, we don't have time to go through all of the 20 algorithms that exist outside of the C++ standard library, but these algorithms are super useful, and I highly encourage you to go check out the algorithms that only exist in thrust because in a lot of cases, they're exactly what you're looking for. Now we're going to move to the third section of our talk, which is focusing on the difference between thrust reduce and std accumulate, and cases where you need to be careful when you are sort of refactoring your code to parallelize it and swapping in one algorithm for another algorithm. So we're going to look at this by, once again, looking at a problem. And this problem is how to sum the even numbers in a list. So once again, I'm going to pause for a couple seconds. Think about how you might do this in C++ using standard algorithms in C++. So the code I'm about to show is only using a single algorithm, and see if you can identify that in the next couple of seconds here. If you are thinking std accumulate, that is indeed what you could use to solve this problem. So unfortunately, there is no accumulate if, which is really what we would want. So you need to basically bake the if, or the predicate, into your binary function object in the form of a lambda here. So basically what we're doing is we have a vector of 3 numbers. The first and last one are even, and we are then going to call accumulate on this range, initialize it to be 0 because we're doing plus reduction, and then our lambda has 2 parameters. The first one is the accumulator and the second one is the value, and so we're always going to be adding to our accumulator, and then we, like I said, bake our conditional into the lambda where we're checking, is our current value even? So modulus 2 equals 0. If so, add the value, otherwise just add 0. And the trick here is, what algorithm do we need to use in thrust when we are writing a parallel algorithm in order to write the same code? And so typically people might think that reduce is the parallel version of std accumulate, so we might want to use reduce. However, there are extra restrictions on reduce in that the lambda, or binary function that you pass to it that's doing the reduction, needs to be both associative and commutative. And because we've baked this predicate into our lambda, it matters the order that we're passing the two parameters. So we can't switch the value and the accumulator, because then we're going to get, we would be performing the predicate on the accumulator, which means we'd end up getting the wrong result. So this is not an associative and commutative operation. So the trick is to upgrade your accumulate to a transform reduce. So what this is doing is basically factoring out the transform into a unary operation, which then gives us a list of the numbers that we want to add and zeros. And then that's just a plus reduction. And a plus reduction definitely is both associative and commutative, so we don't have any problem there. So we have basically two lambdas on either side of our initial value 0 here. The first lambda is our unary object, our unary lambda, which is basically taking our current value and converting it to a 0 if it's not even. And then the second function object, so we don't have a lambda here because this is built into the thrust library. We can just call thrust plus for int objects, and this will do our plus reduction. So the first lambda or function object is always for the transformation, and the second lambda or function object is always for the reduction. And so this is just a really good sort of trick to keep in mind whenever you're refactoring your serial code that's using accumulates. Make sure that the operations that you're doing are both associative and commutative. Otherwise, you need to upgrade to a transform reduce and factor out the thing that's not associative and commutative so that you can get an associative and commutative reduction. And note, I find it really cool to try and compare these things to more functional languages. So really what we're doing here with our reduction or our transform reduce is what we would do in a functional language, where we're basically filtering out the numbers first and then doing a reduction in the form of a sum here. So we don't really have filtering yet in the thrust library as it exists. C++ 20 ranges does have filter. And in the future, in Thrust 2.0, we might have a facility like this. But for the time being, we basically have to do this sort of filtering mechanism by zeroing out values in our transform reduce. And what I think is really cool is when you compare this to our second APL piece of code that we're going to look at, this is actually exactly what you do in classical array programming languages. The plus dot multiplies is an inner product, otherwise known as a transform reduce, where the plus is the reduction and the multiplies is the transformation. And basically what we're doing is we are zeroing out all of the odd values. So the thing in parentheses on the left is basically doing modulus 2 and negating it, which is basically giving you a 0, and then you're multiplying the odd values by 0 so that you end up with a array of basically only the even numbers, and then you're doing a plus reduction on those even numbers. So what we're doing with a transform reduce in Thrust is actually what we used to do in classical array programming languages with inner product. So I think that kind of stuff is super, super cool. Moving on to the second last section, which is getting to the really cool things that you can do in Thrust that you can't do in with the C++ standard algorithms. So the first is going to be looking at algorithms with stencils. So the first question to ask is, how do we do things conditionally with algorithms? The first answer to this is typically using the suffixed _if algorithms. So a bunch of these exist in C++, copy if, remove if, replace if. These are all algorithms that you should be familiar with as a C++ developer, but there's several here that only exist in Thrust, which is gather if, scatter if, and transform if. But all of these algorithms are for when you want to apply a predicate to the same range that you're operating on. So for copy if, you are providing it a range and a unary predicate, and any element that's in that range that you provided is the element that's going to get copied based on that unary predicate. However, what do you do when you want to copy from a range based on another range? So you basically have two ranges, one that is going to be having the unary predicate applied to, and the other one that is going to be copied from. So that's currently not possible elegantly in C++. This is how you would do it in C++, or at least how I would do it in C++. So in this example, we have two vectors, one of pet owners and then one of their pets. So we've got Ashwin, Leslie, and Sarah, and their pets, dog, cat, and dog. And basically what we want to do is we want to collect the dog owners' names. So we want to copy from the owner's vector, but we want to copy based on what's in the pets vector. So one way to do this would be using the standard copy if algorithm, where the first two iterators are to the owner's vector, which is where we're going to be doing the copying from. And then we have a back inserter into dog owners. But then in our lambda, what we have to do here is something that's, in my opinion, an anti-pattern. We're marking our lambda mutable, and then we're capturing an iterator into the pets vector that we're going to be incrementing and basically checking, is the current iterator that we're pointing to a dog? If so, then we do a copy from our owner's vector. But whenever you mark a lambda as mutable, I consider this an anti-pattern because there's probably a better algorithm out there that you actually want to be reaching for. That algorithm doesn't exist in C++, but it does exist in Thrust, and that is the overload of copyIf that takes an extra iterator that's a stencil. So the modified code is basically adding the pets.cBegin iterator, which is going to act as a stencil. And what this means is that the unary predicate that we provide is going to be applied to the pets vector, but the copying is still going to be done from the owner's vector. So this, in another way you can think of this, is almost like we're zipping together the owners and the pets, applying the unary predicate to the pets, and then copying from the owner. So note that our lambda is no longer mutable. We're not capturing anything in the capture list, and we're just checking, is our current pet equal to dog? If so, then we're doing the copy from owners, which this is super, super useful. And like I mentioned before, in functional languages, the way you would solve this is something like this. So once again, this is Elixir, a functional programming language that I find pretty easy to read. First, we're zipping together with owners the pets. Then we're filtering based on the pet, whether it's equal to a dog. And then we're just mapping over our pairs of owners and pets and extracting the owner from that. So this is essentially what you're doing when you do a copyIf with the stencil overload. Taking a look at what this might look like in a classic array programming language like APL, here we're doing something basically which is building up a mask. So we have dog and we're matching this over our pets, and we get back a array of 1, 0, 1, which is basically a Boolean mask that we're then going to apply to our owners using the compress function or algorithm. And note that this is actually something that exists exactly in libcuDF, which is the library that I work on the Rapids team. So there is an algorithm called apply Boolean mask, which is doing exactly this. It takes a vector of Booleans, and then it applies that to another range and only copies the ranges that correspond to basically a true value. So this is a pattern that exists in a modern C++ sort of GPU accelerated library, but that happened way back in the 60s when these array programming languages were coming out. One other example of a place that you might have seen this kind of algorithmic behavior is in the very popular Excel programming model. So here we've got Conor and Jake, and they both have certain monetary values, and we basically want to sum up the monetary values attached to Conor's name. So here we are using an algorithm called SUMIF, which is applying the equal Conor predicate to the column B, but then is summing up from column C. So this is exactly what we're doing in the copyIf example where we're using the stencil overload. So this idea exists in a ton of different places, and it's super, super useful. And I wish these overloads existed in C++ because they show up all the time. One other thing while we're talking about Excel, if you are an Excel avid fan like myself, you might be excited to learn that Excel is now Turing complete because they added lambdas in the most recent version. So there's a great talk by Simon Peyton-Jones, who's one of the key developers and sort of benevolent dictators of the Haskell programming language. And he works at Microsoft, and they've been working on getting sort of lambdas into Excel. And there's a great talk that I would recommend you go and watch if you're interested. And also, Bryce and I had a whole episode talking about my love for Excel if you're interested. So definitely check that out if you want. So these are all of the algorithms that have stencil overloads in Thrust that I know of. I may have missed a couple because I had to go through the 200 or 300 plus algorithms with all the overloads that exist in Thrust. And so if you see it on this screen, it definitely has a stencil overload, but that doesn't mean that I have captured exhaustively all of them. I'll try and get this added to the Thrust documentation. But like I said, stencil overloads, super useful. And if you find yourself in sort of problem where you need to zip together things for the purpose of sort of operating on one range to do something to another range, think stencil and check if the algorithm has a stencil overload. Last but not least, we are going to get to the last section, which is on fancy iterators, which is something that I only really learned about since joining NVIDIA back in 2019. And these are super, super useful. So we're going to hop right into an example that is sort of a simplified version of calculating the first 10 odd numbers. Here we're just calculating the first 10 numbers from 0 to 9 using the Thrust sequence algorithm. And in my opinion, this is a tiny bit of an anti-pattern that I'll talk about in a sec. So an alternative way to construct this vector of the first 10 numbers from 0 to 9 is to make use of something called a counting iterator. So this is a different code that does the exact same thing, where we're basically constructing a counting iterator that starts at 0, and then we're passing that iterator plus 10 to our vector constructor, and then it's generating the numbers 0 to 9 in our vector. And something that's awesome about this code, unlike the previous code, is that you can now use const on your vector if you don't need to modify it later in the code. So this is an anti-pattern that I gave a whole talk about called my least favorite anti-pattern that you can see at the link below. In this talk, basically the anti-pattern that I talk about is ITM, initialize then modify. So whenever you're initializing some container or some variable and then immediately modifying that variable or container, I consider this an anti-pattern. Sometimes you can't avoid it, but a lot of times you can avoid it. You can avoid it using some different language or library facility. And in these cases, whenever you can reach for a fancy iterator, a lot of times you can constify your container. So once again, the reason that I think that this code is better than the code that uses the thrust sequence is that we're able to annotate our vector as const, meaning that we're not going to be modifying it later. So counting iterator is only one of the many fancy iterators that exist in Thrust. Here are the other ones. So we've got constant iterator, discard iterator, permutation, reverse transform, transform output, and zip iterator. So a lot of these correspond to certain algorithms in Thrust and C++ algorithm land. So counting iterator corresponds to std iota or thrust sequence. Reverse iterator corresponds to reverse. Transform corresponds to obviously transform. And a lot of the times, if you are declaring a vector and then immediately calling an algorithm in order to initialize the values in that vector, see if there's a fancy iterator that you can use in order to avoid that ITM anti-pattern. So let's take a look at another example. It's actually the same example that we saw at the beginning of the talk from problem number 1, where we were generating the first 10 odd numbers. So we're going to take a look at APL and how APLers would solve this. So one of the ways they would do this is by starting off with iota 10, so that weird looking I is an iota, which is actually where std iota gets its name from. And this generates the first 10 numbers from 0 to 9. In order to get odd numbers, the first thing we could do is multiply iota 10 by 2, which would give us 0, 2, 4, 6, 8, etc. And then add 1 to each of these numbers, and that would give us 1, 3, 5, 7, 11, etc. And if we take a look at this final expression and sort of break it down, on the right, you can think of this as our iota or thrust sequence. And on the left, you can think of this as our transform. And these are the sort of the corresponding algorithms, but we can also use fancy iterators to get the same behavior. So counting iterator is what we would use for the right, and transform iterator is what we would use for the left. And if you combine these two, you could get a construct called something like the counting transform iterator. And this gets used all of the time in the code base that I work on, libcuDF, in our Rapids project. So this is something that we're going to be upstreaming to Thrust. It doesn't currently exist, but it is a super useful pattern. And it was basically like a bread and butter idiom that was used in APL and other array programming languages back in the day. And I find it really cool that we're here in 2021, literally half a century later, and we've got the same sort of patterns. They're called different things, but you can trace them back to the 60s and how they were building up these expressions. You're starting with a sequence of numbers, transforming them, and then constructing a container based on that, which I think is super cool. So if we take a look at our problem 1 that we saw way back at the beginning of our talk using the thrust tabulate, this is what it originally looked like. Note that we can't declare our odds vector const because we're modifying it when we call thrust tabulate. But if we change this to make use of the make counting transform iterator that, like I said, currently exists in the cuDF detail namespace, but we're going to be upstreaming this to Thrust, we can then get the exact same behavior using the exact same lambda, but now we're able to declare our vector odds const because of that, which I think is super awesome. So once again, there are a ton of fancy iterators. Definitely look into them and familiarize yourself with them. And note that although these come in the Thrust library, you can use these just as easily with C++ standard algorithms. There's nothing stopping you from using them with your C++ code that's not specific to running on the GPU or your device. And I just want to highlight, too, that these were actually initially designed in the Boost iterators library. So if you, for some reason, aren't able to check out Thrust, a lot of these concepts originated in Boost. So there'll be a link in the references.md file to this Boost library that this was sort of originally designed in if you want to check that out. this brings us to the end of our talk. So to summarize, Thrust has many algorithms that don't exist in the C++ standard algorithms that you should definitely check out. They run on both the device and the host, so that's super useful. A lot of people think that they are designed only to run on device or the GPU, but that's not true. They can run on both CPU and GPU. Stencil overloads are super, super useful, and once you familiarize yourself with them, you'll find tons of places where these can be utilized. Fancy iterators are awesome and can lead to more efficient and declarative code. And also be careful when using algorithms like thrust reduce, especially if you're refactoring code from using std accumulate to now using thrust reduce, because there are more restrictions on thrust reduce than there are for std accumulate. And last but not least, parallel algorithms have been added to C++ 17 and 20. So if you aren't able to use thrust and you are using C++ 17 and 20, definitely see if you can make use of the parallel algorithms that have been added. I believe that MSVC, Clang, and GCC all have implementations now. I believe Clang and GCC are sharing the TBB implementation. But if you're using C++ 17 or 20, you should have access to at least a subset of parallel algorithms. So note that all of the algorithms that are in Thrust don't exist now in C++, but there are a subset of them that do. And note that the parallel algorithms that were added to the standard are completely and entirely based on the implementations that started off in Thrust. So super cool to see the work that was being done at NVIDIA led to parallel algorithms being added to the standard. And last but not least, if you enjoyed this talk and you want to learn more about the sort of parallel algorithms in standard C++, check out Bryce Lelbeck's talk, the NVIDIA C++ standard library that talks about libq++, which is a recent initiative that is super awesome. I will leave a link to his talk once it's posted in the references.md file in my GitHub repo once it's posted. And finally, if you want to get started in Thrust, be sure to check out these links, thrust.github.io and the GitHub repo under the NVIDIA organization for Thrust. Thanks for watching, and I'm happy to take any questions in the remaining time we have.